Well, hello. I hear that you would like more information about repeated measures analysis of variance, or ANOVA. Or you're in a class and you're struggling and you need to see step by step, break it down. How do we do this thing? If that's what you're looking for, I've got you covered. This is going to be for an undergraduate class. It might help some graduate students who are feeling a little bit behind, but this is mostly people who have never learned about this before, people who are feeling a little bit lost in their undergraduate statistics class. I teach psychological statistics, and it's, just step by step. How do you get to the point of having a test statistic or an F ratio from a repeated measures ANOVA? So let's start off with when would it be appropriate to perform a repeated measures ANOVA? Now, previously I did a video about the repeated measures or paired samples or dependent samples t-test, and that is when you have two measurements, two means from the same group of participants or subjects, kind of like a before and after, pre and post, or maybe you have two versions of a drug or something like that, and you have people try one version 1 week, then the next week they come back, they try another version, you compare them on that. Those are situations where you have two measurements from the same group of participants or subjects. Well, for a repeated measures ANOVA, you can also use it for that situation, but with a repeated measures ANOVA, you can have more than just two measurements. And so you can have 3, 4, 5. I'm going to stick to examples where we have 3, so we have, as few calculations as possible. So if you had a situation like, let's say you're doing a therapy study, a study on a certain type of therapy, and so you have people beginning therapy, you might get a baseline measurement. And so the patients, they'll get some kind of baseline measurement of, say, symptoms of whatever symptoms you're trying to reduce with the therapy. Maybe they're in therapy for anxiety, and so you do an assessment of their anxiety symptoms. So you get a baseline measure. That is your first measurement. And then you get one in the middle. So let's say it's I'm making things up. I'm not a clinical psychologist. Let's say it's a 6-session treatment. And so in the middle, in the third session, you get an assessment of their anxiety. And then at the end, you get an assessment of their anxiety. And of course, in the real world, it's good to do a follow-up after it is stopped too. So then that could be a fourth, all right? All of those are from the same group of participants. And so since it's the same group of participants and you want to compare those measurements to see if they are different, if they change, then it would be appropriate to use this repeated measures ANOVA. Just had to turn the fan on over here. I'm hoping it won't be picked up too much by the microphone, but it is very stuffy up in this room where I'm filming. I already know that the light is not perfect and things like that, so I'm really hoping it won't pick that up. So, repeated measures ANOVA. It has some things in common with one-way ANOVA, which I went over in a previous video. And so with ANOVA, with analysis of variance, the big thing that's sort of different and unique about it compared to other tests like t-tests that I've taught about is it takes the variance. You have the variance from the study. The total variance from the study is partitioned. And so with a one-way ANOVA, we partition the variance, the total variance, into between treatments or between groups variance and within treatments or within groups variance. All right. With a repeated measures ANOVA, we're going to do further partitioning. And I always like to kind of joke with my students, and they don't always appreciate my humor about that. But I'm like, oh, partitioning is fun. We get to do more partitioning. And I know it's a weird sort of thing to get excited about. I don't know why the camera just went blurry all of a sudden. I think it gets excited thinking about partitioning. All right. So we have already, why are you going blurry? Stop going blurry on me. How dare you? We've already partitioned the variance into between treatments and within treatments. Now, that within treatments, that has to do with, we think of it as our individual difference, our sampling error. The messiness is going to be in there no matter what, and you hope that your treatment does something above and beyond that within treatment's error, or variance, I should say variance, because the word error is going to have a very special meaning in repeated measures ANOVA. We take that, stop going blurry. Well, I'm not doing anything but just sitting here. Don't make me buy high-tech equipment. I don't have money for that. I already paid for a whiteboard. All right, on my professor's salary, that's enough. I'm broke. All right, so stop doing that. It's just going to go blurry from time to time, and I hope you can handle that. Okay, it's acting up. So our variance. Our within treatments variance is further partitioned. It is now partitioned into what we call between subjects variance and error variance. Now, certain textbooks will call this different things. I've also seen it called residual variance. Just keep that in mind. If you're coming from a different class other than one of my classes, your textbook might call it something different. Hopefully you can figure out what the equivalent is with whatever they're calling it in your textbook. All right. Mostly I make these for my students. I can only guarantee I'm covering what's needed for my students. All right. So we've got our between subjects variance. What is that? That is our individual differences, all right? Because the participants in your study, they're going to be different just from being individuals. They're not all going to be the exact same person or animal, depending on what type of study you're doing. So you're going to get differences just from them from being unique individuals. We want to take that out. We want to have the denominator of our F ratio. So if you might remember learning about one-way ANOVA, the F ratio, it's a fraction. It's got a numerator and a denominator. The numerator is supposed to reflect the actual independent variables influence, and the denominator reflecting sort of the sampling error, the individual differences, the things you can't control. All right, with a repeated measures ANOVA, we want that denominator to strictly include the sampling error, the stuff that you can't control in the study, all right, and not include the individual differences, because we know the individual differences are going to be there, but we can take them out because we can see what they are because we're testing the same people, all right? And so we are going to partition the within treatments variance into between subjects variance and error, and the error is what we're going to focus on. So our F ratio is going to look different for a repeated measures ANOVA compared to a one-way ANOVA. One-way ANOVA, the F ratio, you had mean squares. If you don't remember what that is, you're going to have to review your one-way ANOVA. You had mean squares between treatments divided by mean squares within treatments. For your repeated measures ANOVA, it's still going to be mean squares between treatment on the top in the numerator, but we are going to have the filtered, the isolated mean squares error, all right, as our denominator. So it means we're going to need a longer ANOVA summary table. So we have some preliminary computations that we have to do, and we have to set up our summary table. So the first thing I'm going to do is to show you some data. Okay, showing you close up of my whiteboard here. So I have 3 measurements from the same group of participants. So these are students in a statistics class, and I am measuring their ratings of their anxiety about statistics. And so I gave them a 1 to 5 scale. This is made up data, by the way. All right, so on a 1 to 5 scale, rate how scared you are of statistics, 5 being the highest. And so we have measurements at the beginning of the semester, at midterm, and right after taking the final. All right. And so we have, and this is really too small for a real study. I've only got 3 participants, but I want to simplify our calculations. So in the real world, you'd have at least a full classroom, at least, 20 in there, if not more. All right. So we've got our measurements. So this, importantly, let's label these appropriately. This is all student A. Whoops. Hold on. One thing it's helpful to do is to remind yourself that each row is from the same participant. And so this S stands for student. If I had more room, if I would have thought ahead, I would have just written out the word student. So this is student A, student B, or student C. Or maybe you can give them names. It's Allison, Bartholomew, and Charles. All right. And so student A, they go from a 5 to a 3 to a 2. Student B goes from a 4 to a 3 to a 1. You see what's going on here? All right, so we have to remember that these are the same students. All right, because our computations are going to be a little bit different than what we did with the one-way ANOVA. All right, so first of all, what do we need to get? We need to get the totals for each time point. We need to sum up the scores for each time point. Those are going to be our capital T for total. This is similar to what we did for one-way ANOVA, but there's a new thing we need to compute, which is the capital P. Capital P is going to be the total or the sum for each row, each participant. I like to think of it as the participant total or the person total if it's human beings that you're dealing with. So let me go ahead and compute those. All right, so what do we have here? We have our T's. Remember, you just do 5 plus 4 plus 5. That is the T or total for the beginning assessment. The T for the middle assessment is 8, and the T for the final assessment is 4. I put these little symbols, the M and the F, to help me keep track of which one is which. You use whatever system works for you. Now, for your P's, you just add up across the row. So the P for student A, 5 plus 3 plus 2 equals 10. All right, we see how I got those. So you have a P for each row. Each row corresponds to a participant, or in this case, a student. Now, like with one-way ANOVA, you also have to compute your G. Your G is the grand total or grand sum. You can get that by adding up your T's or adding up your P's. They will both give you the same number, which in this case is 26. Now, with one-way ANOVA, right now we'd be gearing up to compute some deviation scores to get our sum of squared deviation scores, but we actually don't have to do that with repeated measures ANOVA. I'm going to show you how to do it in a way where you don't have to do that. But one thing we will have to do for one of our computations is we're going to have to square each individual score. All right, so let's go ahead and get each score. So we're going to do 5 squared, 4 squared. So let me get those written on the board. All right, so in purple, that's our x squared. X is our symbol for an individual score. And so each score gets squared. So we have all of our purple numbers. I know these are kind of bunched up over here, but our purple numbers are x squared, individual score squared. All right, I think we have, one thing we do have to figure out is our K. Do you remember what K is? Lowercase k, for one-way ANOVA, it was the number of treatments, the number of groups, in particular, the number of levels in a treatment, actually. And so in this one, we don't have groups, we have measurement points. So the number of measurement points or number of time points would be your K. So we have 1, 2, 3 measurement points. So K equals 3. All right, so I added a little bit more for our preliminary measurements. We have K equals 3. N, lowercase n, that's the number of scores within each measurement point. In this case, it's 3. And then capital N, uppercase N, is the total number of scores. So 3 times 3 is 9. All right, so I think we're ready. Let's create our ANOVA summary table to fill in. All right, now this beautiful piece of work, I know that's being a little sarcastic, trying to get y'all engaged. This is going to be our ANOVA summary table for our repeated measures ANOVA. So it's bigger than what we had with the one-way ANOVA, and there are going to be more computations. And so we have our source column. We have between treatments, that little TX, that's just an abbreviation for treatments. I'm trying to save space. You are welcome to write out treatments if you're worried you're going to lose track of what that stands for. So you have between treatments, within treatments. Now remember, within treatments has been partitioned into between subjects. BS stands for between subjects here. My students like to joke that it stands for something else, but between subjects and error. Now remember, error is going to be important because that is what we are going to use as the denominator of our F ratio. And then you've got a total row here. So for each of these, we compute sum of squares for each source. We compute degrees of freedom for each source. We only compute mean squares for between treatments an error, and then we only compute one F ratio, all right? So I purposely didn't put the squares here so students wouldn't get mixed up and put stuff there that they don't need to put. All right, so how do we fill these in? Well, the easiest thing to start with is our degrees of freedom. All right, we have our degrees of freedom filled in here, and above each one, I've given the notation of how I computed it, so let me explain for those who need it explained. Remember, I go slow enough so that people who need it explained will have it explained. If you don't need it explained, you're welcome to fast forward or watch me at fast speed. And so degrees of freedom between treatments is K minus 1. K equals 3, 3 minus 1 is 2. Your degrees of freedom within treatments is K times N minus 1. By the way, for these first two degrees of freedom, it's exactly the same as a one-way ANOVA. And so K times N minus 1 is going to be 3 times 3 minus 1. So 3 times 2 equals 6. And then we have our degrees of freedom between subjects. So between subjects, the degrees of freedom equals N minus 1. So 3 minus 1 equals 2 because N equals 3. And then I had to save some space here, but your degrees of freedom error, that is degrees of freedom between treatments times degrees of freedom between subjects. So 2 times 2 equals 4. And then our degrees of freedom total, you can either add up your degrees of freedom between treatments and within treatments, or you can do capital N minus 1. Capital N is 9, so N minus capital N minus 1 equals 8, or 2 plus 6 equals 8. So now we have our degrees of freedom. Now we have to do the part that always takes the most time. We have to compute our sum of squares. So let's get to it. Which one should we do first? I'm going to teach you the way where you do sum of squares total first, just because that's the way I like to do it. It's not the only way to do it. Okay, I know you weren't missing seeing my face or anything like that. I don't know, maybe you were, maybe you're weird. But I like using the tripod so my hands don't shake. But I think we can all see this, and hopefully you can zoom in if you can't see it too well. So this is how we compute sum of squares total. I've got a little T there to mean total. All right, so the formula for sum of squares total for the repeated measures ANOVA is sum of x squared. That's why we had to square all the little numbers, minus capital G squared over capital N. Now the thing is, this value is going to show up in other formulas too. So when you compute G squared over N, you're going to want to save it for later. I circled it over here to be like, hey, you're going to need that later. All right, so the first thing we have to do, the sum of x squared, we have to take all of our little squared numbers and add them all together. So 25 plus 16, where did we get those from? Remember? Okay, so up here, we squared each score. So 5 squared, 4 squared. We squared each score that we got, and then we just add them all together. We add them together and get 94. Now, for G squared over N, G is 26, so we square 26. That's going to be 676. And then we divide by capital N, which is 9. So G squared over N is going to be 676 divided by 9, which is 75.11. We're going to need that in a different formula. That's why I circled it. So we get 94 minus 75.11. The 94 is all of these scores squared and added up. The 75.11 is our G squared over N. So we subtract that from 94 and get 18.89. What do we do with 18.89? Well, we take that over here and we put it in our table. All right, so I forgot to talk into the microphone, but you can see it in blue there. That is our sum of squares total that we have put into the table. Let's get it angled up so we can see the full table a little bit. All right. So we've got part of our table filled in. What can we do next? We're going to have to compute some more of these sum of squares before we can actually get close to computing our F ratio. All right, let's show you how we computed sum of squares between the fan is blowing the wind through my hair. All right, Now we're gonna go to the exciting part, the numbers. All right, let's make sure you can see that there. Okay. All right, so what did we do here? The formula for sum of squares between subjects is the sum of p squared divided by k minus g squared over n. There's that g squared over n again. The good news is we've already computed that as 75.11, so we just plug that in right here. And so we take our p squared. Remember, we had to compute p for each what do you call it? Each person, each student. All right, let's make sure that's on the it's barely on the camera. Okay, I like the tripod so I don't shake too much, but here we go. Okay, so we can see here it was 10, 8, and 8. So 100 plus 64 plus 64 because we squared 10 plus 8 squared plus 8 squared, so it's 100 plus 64 plus 64. That's where we got those numbers from. Those are our p squared. We add those up and divide by 3 because k equals 3. And so we're going to get 228 divided by 3, which is going to be 76. So we subtract 75.11 from 76, and we get 0.89. So then we can write 0.89 up in our table, which I haven't done yet. Give me a sec. All right, so we have transferred our sum of squares between subjects to the table. All right, so what do we do next? Which sum of squares should we compute next? I am going to teach you a way where you now compute the sum of squares between treatments. Trust me, I have a reason. It won't be clear for a while yet. Well, soon it will be, but yeah, I have a reason from going in this order. You don't have to go in this order. This is the way I'm teaching my students to do it. All right, what do we have here? We have our formula for sum of squares between treatments, which is the sum of t squared divided by lowercase n minus g squared over capital N, which again we've already computed as 75.11. So we know that number. We're going to be subtracting 75.11. We need to compute the sum of t squared over lowercase n. So we take our t's. You may or may not remember that our t's were 14, 8, and 4. Remember, t is the total for a particular time point. So the total for the beginning of the semester, the total for the midterm, the total for the finals. And so 14 squared is 196, 8 squared is 64, 4 squared is 16. So we add those up together. We get 276. We divide by 3, and we're going to get 92. So 92 minus 75.11 gives us 16.89. And then we put 16.89 up into our table. And so we can see we have the sum of squares between treatments now. Now we still have 2 more sum of squares to compute. The next one that we are going to do is sum of squares error. And this is where it starts to be a little bit easier. Once you have computed these 3 sum of squares values, it actually gets easier, in my opinion, to compute your within treatments and your error sum of squares. So let's do error next. You're very excited, but here it is. Sum of squares error is, let's get it right up close where you can see it. All right, so all you do to get sum of squares error is you take the values we've already computed, sum of squares total, minus sum of squares between subjects, minus sum of squares between treatments. So we take 18.89, subtract 0.89, and then subtract 16.89, and you get 1.11. All right, now looking at our table. So we have filled in the sum of squares error as 1.11. Now you might be saying, whoa, 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 whoa. We have not computed sum of squares within treatment. It's okay if you didn't notice that. But if you did, you might be saying, hey lady, you forgot a step. You did not show us how to compute that one. It's actually quite simple because the sum of squares within treatments is equal to sum of squares between subjects plus sum of squares error. So you just add 1.11, 2.89, and you get 2 for sum of squares within treatment. By the way, I am rounding to 2 decimal places. That's how we do it in my class. If you're watching this and you're in another situation, not in my class, I can't guarantee you that the rounding will work for you. All right, so now we are almost ready for an F ratio. We need to compute mean squares. Mean squares between treatments and mean squares error. We don't compute any other value. All right, so what we do, to compute mean squares, you just take the sum of squares for that row and divide it by the degrees of freedom. So we're going to compute these 2 mean squares by doing sum of squares divided by degrees of freedom. All right, look at that. We're getting so close to having our test statistic, to having our F ratio. I can feel the excitement coming through the screen. I gotta try to engage you guys. All right, so your mean squares between treatments is 8.45 because 16.89 divided by 2 is 8.45. Your mean squares error is 1.11 divided by 4, which is 0.28. What do we do now? We compute our main result, our F statistic, our F ratio, which is mean squares between treatment divided by mean squares error. So let's go ahead and compute that and fill it in. All right, so we divide 8.45 divided by 0.28, and we get 30.18 as our F ratio. All right, so is this a good result? What do we do with this result? Remember that your F ratio, it's what we call an omnibus test statistic. It detects whether or not there is any mean difference whatsoever when you compare the means for these 3 time points. We need to know if this is statistically significant. So if you were using software to compute your F ratio, it would probably give you what we call a p-value, a probability value, and typically we want our probability value to be less than 0.05, meaning our alpha is set to 0.05, meaning we want less than a 5% risk of making a type 1 error. In my class, typically we're by default, we use alpha set to 0.05. I don't know what your situation might be. And so how do we know? How do we know if this F ratio is large enough to be considered statistically significant, or that it has a p-value, a probability value less than 0.05? We need to look in an F distribution table. All right, before we look at our F distribution table, we do need to know some information. First of all, we need to know our alpha level. I've said that we're going to use 0.05 as our alpha level. We also need to know our degrees of freedom. In particular, we need to know degrees of freedom between treatments and error. So 2 and 4. We need to remember 2 for our numerator. You just got to see my messy office a little bit. And here we go. I'm looking on my laptop screen because I like to use the F distribution table from this website. There's also one in the back of many statistics textbooks. All right. So, alpha 0.01. We don't want that. We want alpha set to 0.05. So we are looking at the correct table. And we find on the top, we look for degrees of freedom of 2. And then on the vertical column, we look for 4. And then we line ourselves up. And hopefully you can see that that lines up with 6.94. What the heck does that mean? 6.94. All right, that 6.94 is what we call our critical F, our critical value for F. And sometimes we abbreviate it with F with the subscript crit. And so the F crit is 6.94. What does that mean? You need to get an F ratio of at least 6.94 for it to be considered significant with alpha set to 0.05. Our F ratio was 30.18, which is higher than 6.94, which means it is statistically significant. Yay! How would we write that in APA format? All right, I'm running out of space. I put it right here. So you'd put capital F, italicized, and then in parentheses, your degrees of freedom, 2, 4, equals 30.18 And then after the comma, you put your statistical significance information, p less than 0.05. If the p is less than your alpha, that means that you have a statistically significant result. So that means our overall or omnibus result is statistically significant. That means there is at least one significant difference among the means for each time point. Now, in real research, we would also be interested in performing post hoc tests to see where the differences are. Is it beginning significantly different than middle, but not significantly different than final? Or is it all three of them significantly different? We don't know where the difference is, just that there is at least one difference in there. I'm not going to go over post hoc testing for this video. This is just to make sure you can compute that main result, the F ratio. Also in real research, you would very much be interested in computing effect size, which we are not doing in this video, and I'm not teaching my undergraduate students how to do, at least not by hand. And so if you need to know that, you'll have to find somebody else who's done a video about that. This is just about how to get the main result, the F ratio, for repeated measures, ANOVA. I hope you had as much fun as I did. Isn't this beautiful? I'm going to hang that on my wall. All right, folks, happy computing. And if you are doing this to prep for your final exam, like I'm sure many of my students are, much luck to you. And you're gonna do well, and you're gonna kick statistical butt.